Okay, so thanks very much. I will start by just recapping where we got up to at the end of last time. We're looking at a nonlinear signal model on a world-sheet to the Riemann surface, with assuming that it has an isometry with a Killing vector k, which preserves also h. And we're looking at gauging the isometry. And the reason for doing this was we were going to try and understand t dualizing in the direction corresponding to k. We found that we took the action, we added Noether coupling plus a term quadratic in the gauge fields. We got something whose variation was like that. And remind you that this vector v was determined by taking h, contracting it with the vector k, two form. And then because it followed, we saw that it followed from this equation that two form was closed, and so that locally at least it was d of some v. And we saw that the gauging was only possible then. This could not be counted in any other way, so it required, for the gauging to be possible, it required that k dot v was 0, and also for the signal model with the couplings in this in S prime to be well defined, it turned out it required the one form v to be globally defined, so that this was in fact exact, so that v was a globally defined form. Then we saw that you could get around these obstructions by introducing an extra scalar field whose variation was something which looked like this, so it could cancel against this variation here. And as a result, an invariant action took this form, and this is where we got to at the end of last time. And people have asked about references. So in this treatment of the case with a single vector, I'm following a paper from '93 by Alvarez, Gomez, Barbon, and Gonzalo, who are among the first to look at the global properties of T-duality. So we had this invariant action from the last slide. I've written it out again. And I remind you that the form of these Noether currents J and J bar are such that when this looks like this, and J plus grad bar chi looks like this. So notice that here we get the combination V plus grad chi and minus V minus grad chi. So the effect of introducing the chi has effectively shifted V to V plus D chi. So that's because chi only occurs through here and here, and so only through shifting V in this way. So before, the problem was that we needed V to be globally defined on the d-dimensional space, but now V occurs in the full combination V plus D chi, and require this to be globally defined on this bigger space with coordinates, with d plus one dimensional space, but it's corresponding to the d-dimensional space with coordinates x, and its extra coordinate chi. And here we don't need that V to be globally defined because we've got some ambiguity here. We can shift V by D of something and then compensate it by a shift of chi by minus that something. So this means that V could be a connection, and here what we could be looking at a generalization where we're setting up a circle bundle, or a bundle whose fiber coordinate is chi. We'll see in a moment that it's chi as a circle. And V would be a connection on that bundle. So what we're seeing is that that the V no longer needs to be a globally defined one form, but could be a connection. And so it's enabled us to look at a more general setup. And we talked last time briefly about large gauge transformations, and I claimed that invariance under that required that chi be periodic. So we can see that in more detail now. So the terms involving chi are gauge invariant under infinitesimal gauge transformations, or invariant up to given invariance of the action up under gauge transformations up to a total derivative term. And we need to check what happens with these total derivative terms, in particular what happens under large gauge transformations. So we've got a genus G world sheet, sigma G, with, and there are compact isometry orbits on the target space. We could have large gauge transformations where the parameters have got, which are scalars on the world sheet, can in fact have winding number around a one cycle gamma. So the integral of d epsilon to be written as giving rise to some winding number, which would depend for each which is some integer, and this would there'll be such a winding number in principle for each non-contractible one cycle. So, for example, if we looked at a torus, the case G equals 1, the case for higher genus works similarly, but it's formally a little more complicated. The variation of the action it gives a total, what's locally it looks like a total derivative term, but it isn't quite a total derivative term because these epsilons have got winding, and so these epsilons are not globally defined, so you can't integrate by parts the derivative of the epsilon because the epsilons are not globally defined. So this is just rewritten in this way. And the torus has got two non-trivial cycles. We call them the A cycle and the B cycle. One through round one circular dimension, one round the other. And so this has got, it takes this form. Now the integral of, so there are two, so you've got the winding number of epsilon around the B cycle here, and the winding number of epsilon around the A cycle. And we see that this will vanish if, if what chi is, if chi is a compact, if chi is a periodic scalar, and which can also have winding, then we'll see that if chi is periodic with period 4 pi, then d chi, the integral of d chi could give a winding number m, and then you would get a factor here which would give, you would get 2 pi times 4 pi times an integer divided by 4 pi. So we get 2 pi I times an integer. And so the action would shift by 2 pi I times an integer. And so e to the minus action would be invariant. And so the quantum theory would be invariant if we had this as periodic. And the reason why it's coming out as 4 pi rather than 2 pi is because of the units we chose for alpha prime. If we'd have halved alpha prime, we'd have changed that. So to see what's going on a bit further, we can introduce adapted coordinates. So if we introduce a coordinate theta along the orbit, along the killing vector, so that moving in the killing vector direction corresponds to shifting by theta, so we have coordinates theta and then d minus 1 other ones. So our original manifold is a d-dimensional manifold with these coordinates. So you constructed a bigger manifold, let's call it M, which has got the extra coordinate chi. And so this is, in fact, as we've seen, it will be some kind of circle bundle over M, whose connection is related to this vector field, to this one form V we introduced. We can also regard this M as a torus bundle over B. So you've got now the coordinates x as the base space, and then you've got two circular coordinates theta and chi. So giving a torus, a two torus bundle over B. We can think of it in two different ways. And we have a nonlinear sigma model on this d plus one dimensional space with these three coordinates here. And by an argument similar to the one we had yesterday, this gives rise to two different nonlinear sigma models. Essentially, this has got a gauge invariant, and the gauge can be fixed in two different ways. One which gets rid of theta, and one which gets rid of chi. So both ways we either get rid of theta or chi, and we keep, and we also get rid of the gauge field. And in those two different ways, we give rise to either the original sigma model with coordinates theta and x, or a dual one with coordinates chi and x alpha. So how does this work? So the first way of doing it is to integrate out the Lagrange multiplier field chi. So this implies, first of all, it implies the splitting chi into a globally defined piece and a piece with winding. We saw that integrating out the globally defined piece imposed f equals 0, and that integrating out over the winding modes gave the constraint that there are no Wilson lines for the vector field. So we've got a flat connection with no Wilson lines, so we can then gauge it away completely, and we regain the original sigma model on M. We've got rid of both A and chi. On the other hand, if there are no fixed points for the isometry, then we can gauge away chi. Sorry, there should be a chi here. Gauge away theta. So there should be a theta here. then we can then integrate out A, which appears algebraically, to give a model on the dual space. And this has got, so we're left with a manifold which has got these dual coordinates, chi and x. So we've got two different d-dimensional manifolds, one with coordinates theta and x alpha, and one with coordinates chi and x alpha. And these are the dual spaces. And if one reads off the couplings, we find that the new metric and B field for the x tilde space, if we're using 0 to denote the chi direction, then these have got to take this form. And you see they're explicitly in terms of k's and v's. And k squared, I remind you, is just the norm of the killing vector with respect to the metric gij. So here we have the explicit form of the Boucher rules for the transformation of the metric and the B field under T-duality transformations. This generalizes to the case where several killing vectors. Here we can try and look at the possibility of repeating this argument if you've got some more general isometry group. So suppose we've got a set of killing vectors labeled by an index m. So there's a number of these. In general, they'll generate the isometry group. It might not be the full isometry group, it might be some subset of the full isometry group. But they're closed under the Lie bracket, so the Lie bracket of any two vectors gives another vector, so we get to the Lie algebra of symmetries. And we require that the Lie derivative with respect to each of these vector fields is 0. And as before, we see that contracting with Km and using this fact will give rise to this being locally exact, so that locally at least there's a Vm for each vector field corresponding to each killing vector. And in these papers with Bill Spencer long ago, we showed that the gauging is only possible if its VMs are globally defined, so this is exact, and this is antisymmetric under swapping n and m. So in the case when there's only one killing vector, this was saying that the k dot v would be 0. So now we're seeing that km dot vn has to be antisymmetric under interchange of m and n. So now we could try and extend that and try and look at the possibility of having the argument we had before to try and look at T-duality with respect to this isometry group. Again, we could add Lagrange multiplier fields and gauge fields to gauge all of these isometries. But now, in general, this would be a Yang-Mills, be a non-abelian gauge field strength. So this would be dA plus A wedge A. So this would set F. If we use this kind of coupling, this would set F to 0, but it would not eliminate the Wilson lines. And so setting F to 0 would not enable us to gauge away the vector fields and wouldn't get us back to the original model. So it doesn't give the duality for the same reasons we saw yesterday. If we tried to do the alternative thing of the kind of expression we used before, we could, which is in the abelian case related to this by an integration by parts, this was something which would only be gauge invariant for the abelian case. There's no way, if in the non-abelian case, the A wedge A term here would lead to problems, and there's not any sensible way of doing that. So the attempt to look at a non-abelian version of T-duality doesn't give an equivalence between the dual equivalent sigma models. It only gives an equivalence in the case of, it only gives a correspondence between sigma models, which is a map between them, but it doesn't lead to an equivalence in the way that we had here. So remember, the key idea we had here was we had a master action as a gauge sigma model on a D plus one dimensional manifold. Gauge fixing in two different ways gave rise to the two dual models. So they were both different, the same model, the same original model written in two different gauges. So first of all, to get some version of T-duality to work here, we want the group to be abelian, and we also want it to be compact with U1 to the ends, and then we can see whether we can add extra fields, we can get around the obstructions to the duality. So it turns out if you're trying to do a duality with respect to all of these killing vectors at the same time, then it turns out that there is an obstruction which are weaker obstructions to gauging, but they're still ones which are possible. So that there's, first of all, that 3 contractions of the H with 3 killing vector fields is 0. And secondly, the contraction with 2 killing vector fields, Km and Kn, is something which is exact, so that there's a well-defined function, Bmn. And under those circumstances, the gauging, the T-duality is possible. And this will now, so I want to now say briefly the geometric form of the Boucher rules. So where they're often presented is in terms of fractional linear transformations of metric plus B fields. And I showed some of those forms yesterday. There are problems in that. First of all, these are tensors, and these transform under diffeomorphisms. So the probabilities of that under diffeomorphisms are rather problematic. One could get around that by using frame components. There's still a problem then because the B field is not a tensor, it's a gauge field. And the kind of transformations that we looked at for the for each G plus B would be inconsistent with the would run into problems with the gauge transformations, and it's not at all clear how to make that work. So what I want to do now is find the right variables to express the T-duality in terms of to give a well-defined, so to reformulate them in terms of well-defined geometric structures in this case. So we could define a metric essentially on the orbits of the killing vectors by taking the norm of the inner product of Kn with Kn. So this is a d by d metric for the d isometries. So we can now we can also define a set of one forms in this way, and I'll be assuming here that GMN is invertible, which would be the case provided that K doesn't have any the killing vector, the isometries don't have any fixed points. At a fixed point, K will vanish, and this will not be invertible. And so that's where the constraint of looking at isometries which act effectively without fixed points comes from. So then we get a set of one forms that got a lower index here, and I've chosen to raise this index with this. And we defined a set of, and so we can define a set of two forms given by the curls of these one forms. And the metric can be written in terms of these one forms plus a piece which is orthogonal to the killing vectors. So the metric with respect, the inner product with respect to this G bar is orthogonal to the killing vectors. So if we're thinking of these, this is giving a fiber bundle. We've got these size of one forms corresponding to the fibers, and this gives a metric on the base, essentially. So we say that G bar is a basic quantity. And in adapted coordinates, where if we introduce coordinates xn corresponding to these fibers, these killing vectors, then these size can be written as dx plus some a, where these a's are dependent on the coordinates on the base, one forms on the base, and dA is f from here, and we see that these a's are giving a connection on a torus bundle over the base space. And the constraints on H then imply that there's some globally defined functions, BMN, such that, and that H can be written in this form, where this F tilde is defined from one contraction of H with a killing vector, and gives rise to something which is closed, and so this psi tilde is typically of the form like this, where x tilde was the extra coordinates. So we find that we get a structure for H like this in terms of a dual connection A tilde. So A tilde is a connection on a dual torus bundle whose fiber coordinates are the x tildes. And so from the B field, we're constructing another vector, another circle bundle over the base, which will be the dual bundle which will be swapped under duality with the one we got from the original base.
Chris, can I ask? Can we go there? I thought so. The T-duality works when triple and double contraction equal to 0, at the level of sigma 1, right?
So it requires not that this is Yeah, but it works under weaker conditions where this is exact.
You cannot gauge it, right?
No, you can't gauge it, that's right.
But how do you get your T-duality?
Because you can gauge it, well, you can gauge it because you've introduced extra coordinates. If you remember, when we started off with one Killing vector, we found that there were obstructions to gauging, which you could get round by introducing the extra coordinate chi. So now we've got these x tildes being the corresponding thing to the extra coordinates, and we can do that, and that enables us to do the T-duality.
So you can gauge it by introducing this extra guys. You can gauge it.
Yeah, subject to these constraints. So you can't always gauge it, but you need these constraints to be able to do that.
Because, well, if I'm talking about the topological T-duality, the standard story, then I remember you're supposed to have this term h bar plus next term. This extra term dB doesn't work, and you talk about topological T-duality.
Yeah. Well, the dB, the B is one which is written in this form in terms of something global. So this is something which is exact. It's an exact piece, and its importance is an exact piece here. So maybe the topological T-duality doesn't care about exact pieces.
Yeah.
As we'll see in a moment, this BMN plays an important role in the T-duality transformations. So we have, so under the T-duality transformations, it's this G, which is the frame component, essentially the metric determined from the Killing vectors, and the norms of the Killing vectors, and there's BMN, which we just described. And it's these things which transform under T-duality under fractional linear transformations. And it also swaps the two bundles around. It swaps F and F tilde, and the bundle corresponding to the original torus vibration, and the dual one which comes from the B field. And under these T-dualities, then we get the metric goes to a T-dual one, where we're replacing this, the size by psi tildes, and we're replacing this G by a G tilde NN, which is determined by the symmetric part of E inverse, and the similar transformation from the H's to the H tildes, where this, the B tilde is the antisymmetric part of the E inverse. And here we see these are equivalent to the Boucher. These are the reformulation of these standard Boucher rules, but written in a way where it's intrinsically clear what the geometric meaning of all these terms are. And so one can see that as well as turning the geometry, we're changing the topology. There are two different bundles, one corresponding to the F, one to the F tilde, which are being swapped around by this T-duality. So far I haven't talked about the dilaton. I was just looking on the case of a flat world sheet, but now if we were to reinstate the dilaton, which occurs through the Frekkin-Satelin term, then integrating out the world sheet gauge field gives rise to a contribution, which is a formally the functional integral gives rise to this formal determinant, which involves a product over each point on the world sheet. And one can show that a careful one-loop calculation of this results in a shift of the dilaton. It gives rise to a curvature on a curved world sheet. It gives rise to a curvature term, and as was shown by Satelin and Schwartz, and this gives rise to a shift of the dilaton, which could be written in this way. So under T-duality, it's one of the transformations of the metric and B field as this transformation of the dilaton. And that gives rise to a conundrum. We see that the dilaton shifts under T-duality, but we also know that the dilaton expectation value gives a string coupling constant. The string coupling constant is usually described as being exponential of the expectation value of the dilaton. And the reason this comes about is if one looks at any string interactions, one finds at any loop order, one finds that the string coupling constant always occurs in a combination of the coupling constant times e to the phi, which means that the string coupling constant can effectively be reabsorbed into the constant part of the e to the dilaton. And so one can set the string coupling constant to 1, and then effectively e to the dilaton would be the string coupling constant. But then there's a problem, because T-duality is claimed to be a perturbative symmetry, but here we're seeing that it changes the string coupling constant, which seems to be a certain tension with that. On the other hand, it's meant to be something which is a symmetry order by order in the string perturbation theory. And there's a nice resolution of that, because it turns out that the combination e to the minus 2 phi times square root of the determinant of the metric, or the modulus of the determinant of the metric, is invariant under T-duality, and I'll call that e to the minus 2d. So this is not a scalar, this is a density, because of the square root of def g. But nonetheless, the exponent, because this is invariant under T-duality, you could imagine using this as a string coupling constant. It's clearly related to this, proportional to this, but it's invariant under T-duality. And in fact, a careful examination of what happens, for example, in string field theory, shows that it's precisely this which arises as the string coupling constant. And that...
Sorry, but in different coordinates, value of d will be different.
Yes.
Is it a problem?
It's not a problem. That's a good point. Let's.
So a very simple example, which we both know, is generalized scalability, right? In complex coordinates, you can choose this combination to be equal to 1 or whatever.
So one way of saying what happens is when one looks at the picture where one includes the form of this thing which arises from string field theory, one finds that one's effectively using a double picture, and one finds that everything works out fine, and everything works as invariant under T-duality, but this is the coupling constant. But then one has to make some choice as to which half of the coordinates one's using to be the space-time coordinates, essentially what I refer to as choosing a polarization. And when you make that choice and then re-express it in terms of those variables, then one finds that under the change of variables, one finds that one ends up with phi rather than d, and then the diffeomorphisms one gets as a result of that gives rise to other things which you look at there. Before one makes that choice, one doesn't have diffeomorphisms in the standard way, but one has these so-called double diffeomorphisms, which I'll talk about tomorrow. So, but it's interesting that there's a tension between the T-duality and the diffeomorphism invariance. And when we look tomorrow at a formulation which is T-duality invariant, we'll see that the diffeomorphisms are replaced by something more general. And we'll have the properties under that, but not under the... And we'll see that this transforms under as a scalar under those things. Thank you. So I'm now going to turn to the next topic, which is to looking at non-geometric string backgrounds using these duality transformations. These could arise as T-duals or mirrors of conventional flux compactifications. And one thing which I find interesting about them is they're intrinsically stringy, and things which can't arise in supergravity, but are perhaps a simple extension of what arises in supergravity. And it gives, so it's a simple example of something which gives rise to new kinds of stringy geometry. It gives more compactifications, which typically fix some of the moduli which are often hard to fix. And in fact, the list of generic four-dimensional supergravities to 10 or 11 dimensions is intrinsically non-geometric. Only special ones arise from geometric compactification of higher dimensional supergravity. So the embedding of generic supergravities in string theory will require these kinds of compactifications. And in fact, generic solutions of string theory appear to be of this kind, so that maybe the kinds of things we've been looking at for the supergravity solutions are just perhaps the tip of the iceberg. So the idea is, if we start off with a geometric background, which is a manifold equipped with various tensor fields, fluxes, and gauge fields, and perform a duality, and in the context of this talk I'll be talking about T-dualities only, then it can give rise to a non-geometric background. So the dualities are stringy symmetries, which are usually maps from a conventional geometric background to a new one, and that's what we saw in the context of the Boucher rules. But sometimes it's not. So sometimes in these cases where there's an obstruction to the duality, one can still thought of the kind which we looked at. We saw that there are obstructions to the Boucher rules, forming the Boucher rules as arising from gauging signal models and manipulating those. Nonetheless, there are cases where one can formally try and use the rules and see what it gives, and it gives rise to something which would formally give rise to something which isn't a conventional background. So we can either take 2 points of view. One is to say that there's an obstruction to duality and you just shouldn't do it. Or another possibility is to say that there's in fact some kind of non-geometric background arising, and we're going beyond the usual rules. And what I want to do is I want to provide some evidence in favour of this second possibility. So that's exactly what string theory tells us we should do. So the idea is this. So suppose we had a space which is decomposed into local patches of space-time, and we're gluing the physics together in the overlap using geometric symmetry, using diffeomorphisms and gauge symmetries in the conventional way. Now, suppose in that structure we now perform a T-duality. So we're assuming that this space, these fibers, are all got the form of these patches have all got the form of torus vibrations, so that there's isometries we can do a T-duality with respect to. And as a result, we can typically, even though these are started off with being conventional diffeomorphisms, acting on diffeomorphisms with T-duality, we saw that the diffeomorphisms were some of the diffeomorphisms were part of the group ODDZ. They were the general linear subgroup. And acting with T-duality conjugates that subgroup within the ODD group, and general will give something outside the geometric subgroup. So we'll end up with transformations which can involve proper T-dualities. And we'll see explicit examples of this. So this means that starting off with something like this, under a T-duality, we end up with something where we're forced to glue together using T-dualities also, to form what I refer to as a T-fold, where the patching uses T-duality, and the physics is smooth across the patching because the T-duality is a symmetry of the theory. So here's a cartoon of what I'm suggesting. If we have a space which is something like a large circular radius r times some other stuff, which I'm reflecting as a cylinder, we've got another space, another patch which looks like a small circle of radius 1 over r times some other stuff. What this is saying is we could try and glue this big circle to this small circle, but relating the things by T-duality. So we're gluing a momentum mode here, which is light, to a winding mode here, which is light, and a heavy winding mode here to a heavy momentum mode here, or linear combinations of those. So clearly, joining something like this to this, you can't make it smooth in conventional geometry, but nonetheless, just such a thing is possible and arises in string theory. And now, by now there are many consistent non-geometric string backgrounds which exist in the literature. Here's a very partial list of some of the ones some of the early ones which occurred. So some of them arise as orbifolds or asymmetric orbifolds. So in particular, some of these non-geometric backgrounds have moduli spaces. At particular points in the moduli space, some of these non-geometric backgrounds reduce to asymmetric orbifolds, which of course are simple examples of things which can't be understood eventually geometrically. And also generalizations involving U-duality and mirror symmetry, which I referred to yesterday. So some of the first examples involved setups where you had T-duality monodromies around degenerate fibers. Another is a case where, so these are the cases where you have a torus vibration over a base, and there are singularities where they're corresponding to points in the base where the fiber degenerates. And as one goes around the base, one goes around these singular points, then one finds that the fibers are glued together using a T-duality transformation, and so one gets a T-duality monodromy around these singularities. And another kind of example, the ones I've looked at with Atish Stavelkar, where one compactify, which is essentially a stringy lift of Schwartz compactification, where one compactifies on a string theory on a circle or a torus, and allows T-duality monodromies as one goes around those circles. And these are the cases where special points in the moduli space, these are reduced to asymmetric orbifolds. So these might be things for looking at some generalizations of phenomenology, where one has internal non-geometric backgrounds giving rise to, nonetheless, to a conventional four-dimensional field theory on compactification. And as I mentioned, the lift of generic four-dimensional supergravity theories will often involve just such a higher dimensional space. So if one was to pursue the landscape point of view, where one tries to count number of kinds of models in a landscape, then it seems that one should really try to also include T-folds and more general non-geometric spaces in the counting, and not just Calabi-Yau's, and giving rise to more general kinds of structures. And some of these non-geometric backgrounds turn out to be much better than conventional models in giving rise to moduli stabilization. In particular, one example is a paper which given a space of compactification where all moduli are frozen. So let's look at this in a bit more detail. So we're looking at a case where you've got two patches, where each of which corresponds to a patch on a base with a torus fibered over that, and another patch on the base with tori fibered over that. So that the E, which was the metric plus B field, would vary with respect to the position on Y here, and would vary with respect to the position Y primed here. So for a geometric background, G plus B would be tensorial plus the antisymmetric tensor gauge transformations. But if we just forget the antisymmetric gauge transformations and suppose that B was a tensor for now, just to simplify the argument, then the patches would be glued together using geometric symmetries. For example, using GLDZ transformations, which rotate the D coordinates on the tori and their integer valued matrices, because in order to preserve the periodicities of those coordinates. Then, after doing a duality transformation, the transition functions will now be T-dualities, and we'll end up with E and E primed in the overlap being related by a fractional linear transformation. And so we'd end up with something after a T-duality of a conventional transformation would then give rise to a conventional manifold, would give rise to a T-fold. And this would be something which is rather strange, because these gluing things would mix together the metric and the B field in a very non-trivial way. And as we saw, they'd also relate the vector fields describing the vibration here to the ones describing the B field over there, and vice versa. But nonetheless, the physics should be smooth. This is a T-duality symmetry, and in general, this will be taking us outside the things which would be allowed by the Boucher transformations and giving rise. And this would be a way. These kinds of setup gives an example of the kind of thing where there are instructions to perform in the Boucher dualities, and this is expressing what precisely ought to be going on there. So let's look at this in more detail. Let's look at a particular example. The famous example, which is looking at a 3 torus with a constant H flux, which is an integer times the volume on this 3 torus. Now, this isn't a conformal field theory, but it can be seen as part of a conformal field theory. There are examples where one has such a 3 torus with flux fibered over some base, and by embedding this in a bigger geometry, one can find a conformal field theory. But I'm just focusing on this part of the solution, just for the purpose of these lectures, just to see precisely what happens to that. So if we regard this as the product of a circle times a 2 torus with coordinates x and y, z, we can choose a gauge for the B field, which is a constant plus n times x. Byz is constant plus n times x. So then the curl of that will be the derivative of that with respect to x, which would give rise to that n. So if we take a t-dual of this on the z circle, so we've got three circles. So we choose one of the circles here, which is one of the coordinates which B doesn't depend on. So that here, shifting z is clearly going to be a symmetry of that setup. Then we end up with a setup where h is 0, but then it's now a non-trivial fibration of the two torus over the circle. It's no longer a simple product, but there's a fibration. And what's happened is that now the topology in the B field, which was having a non-vanishing H, has been replaced by having a topology in the bundle over this two torus over the circle. It's an example of what we saw before about T-duality switching the topologies of those two things around. So in particular, if tau is the modulus of this two torus, the complex structure modulus, this will now depend on x. And as we go around this circle, the two torus will come back to itself by an SL2Z transformation, which the SL2Z acting on the modulus tau. So this is a large diffeomorphism of this two torus. So going around here, we end up with the same two torus, but the coordinates on that are related by a large diffeomorphism in the modular group SL2Z. And this three-dimensional manifold, which is given by this two torus bundle over a circle, is related to the famous it's related to the nilfold. It's the nilfold, which is a famous three-dimensional space which arises from the Heisenberg group manifold, identified under a discrete subgroup to make it compact. So now we could ask what happens if we now t-dualize on the z circle. We just get back to where we started. We just undo the t-duality we just done. But we could, so things depend explicitly on x, but not on y. So we could now ask what happens if we do a t-duality in the y direction here. So now there's an issue because if one looks at the y killing vector, it looks as if shifting by y gives a killing vector. But in fact, it's only locally defined. And because of the twists, if one looks at it closely, it turns out that the vector field one would try to be using as a killing vector is not globally defined. But we could try and use the rules, and so this would be a case where the Boucher rules wouldn't apply, but we could try and use them anyway, and by applying them locally into the fiber-wise duality, because locally on this x, I mean, it looks, if this was a very large circle, for example, and things were varying slowly with respect to here, one would expect to be able to still be able to do the dualities fiber-wise. So let's see what happens if we were to ignore the fact we shouldn't do it and see what happens. Then we end up with something which looks like another kind of torus bundle over the circle. But now we have a very strange metric and B field, which involve strange dependence on the coordinate x here, which looks particularly strange when you remember that x is meant to be periodic. And these are clearly not periodic functions. But what's going on here is that now if one looks at the metric plus B field, and looks at how that changes as one goes from x to x plus 2 pi, as one goes around here, what one finds is that the metric and B field come back to themselves by a t-duality transformation, by one of these strange nonlinear transformations, for some O22Z transformation. And so this is giving an example of something which is a t-fold. So here we see that if we were to go ahead and assume that we can do the t-duality, even though we, strictly speaking, shouldn't, then what we end up with something, and using the physical example, that one should be able to use the duality fiber-wise, locally on the positions in X space. I mean, that's a familiar argument going back to Witten and Buffer, who's been used in many examples. So if one used to use fiber-wise duality, then one's forced to accept that there should be a t-fold arising in this way. And so this would be a simple example of this. One could also ask about what would happen if one tried to do a T-duality in the x direction. And one of the problems there is there isn't an isometry, there's explicit dependence on x, so there isn't an isometry with respect to x even locally. And so this would seem to be even further away from something one could try and do within the context of T-duality, but we'll come back to that point later. So before that, I want to talk about how one reformulates all this in what I refer to as a double formalism. I argued yesterday that it's natural to augment the coordinates x with double coordinates x tilde on the torus. These are the things we saw arising from, whereas the x is a conjugate to momentum modes, these are conjugate to winding modes. And we saw that these naturally arise as the extra coordinates one needed to be able to gauge the signal model, and then be able to end up with a master action which could be gauge fit in two different ways to give the two dual forms of the theory. So these coordinates will transform linearly under ODDZ. So these are just double coordinates on the torus fibers. And a T-fold transition would mix these two together so that if there's a non-trivial T-fold, then it could be a setup where there's no global way of separating the real space-time x from the auxiliary space coordinates x tilde. And in that case, there'd be a topological mixing between the two, which one couldn't undo. And that typically is what happens in T-folds. And what I'm going to be looking at is a duality covariant formulation in terms of these x's, where one sees these transition functions of ODDZ embedded inside diffeomorphisms on this double torus. So whereas these things looked very non-geometric when formulated in terms of the original D-dimensional torus, in terms of these double torus, they'd appear naturally as a subclass of the diffeomorphisms on this double torus. And this would give, in this way we'd be able to, by doubling the fibers, for a T-fold there'd be a double torus bund setup where one would have a good torus bundle over the base space, even though of the double torus, but not of the original one. So what we're doing is we've got some base space, and before we just had a D-dimensional torus fibered over the base, at least locally. Now we're doubling that, as well as having the dx's, we've got the dx tildes occurring on the base, on the fiber. And what we'll aim to do is construct a duality invariant sigma model on this double space. We're doubling the fibers, but not the base. So we've doubled the degrees of freedom up here. So we need to make it equivalent to the usual formulation, we need to halve the degrees of freedom again on each fiber. So in the free case, this was x and x tilde were related by this condition, which meant that the x derivatives of x tilde could all be expressed in terms of the x's. And so in that way one would eliminate the x tilde degrees of freedom in terms of the x's. So this constraint was what halved the degrees of freedom in the usual case. So in the general case, there's a generalization of this involving, I'll explain what these derivatives are in a moment, and what this matrix is. But this matrix is something which depends on the position y, and it starts off looking like this. So when it's precisely this, then you restrict to this constraint. But there's some extra y dependence. So we've got this tensor which squares to +1. So it's like a complex structure, except it squares to +1 instead of -1. And it projects onto things which are either +1 eigenvalues of S or -1 eigenvalues of S. As we'll see, the +1 eigenvalues of S are right movers and the other ones are left movers. So what this means is that these coordinates are split, these 2D coordinates are split into D right movers and D left movers. And which half is which half is split are the right movers, varies as we move over the position in the base, because this matrix S depends on the coordinate on the base. And to recover the conventional formulation, we would look at a splitting of the double coordinates into original coordinates and the dual ones. So in other words, we're trying to pick a real space-time, which is the D torus sitting inside the 2D torus. So here we have a caricature of a cartoon of the 2D dimensional torus. So we've got the x directions and the x tilde directions. And we're choosing a subset of these, say the x directions, to be the real ones. So we're picking space-time as essentially a slice through there. And T-duality acts as to rotate the polarization. So instead of choosing the x's as the real space-time, we could have the x tildes as the real space-time. And the T-duality symmetry means that the physics should be independent of which half we choose as the real degrees of freedom. So for a T-fold, one way of thinking about it is this. We construct this nice double torus bundle, which is a good space over a good manifold. And over each patch in the base, we need to pick a polarization. We need to choose 1/2 of the degrees of freedom to be the ones we're identifying with conventional space-time. And so 1/2 to be the x's, the other half to be the x tildes. And T-duality transitions in the overlap would mean that in general, there would be a rotation of the polarization as one went from one patch to another. And a geometric background would be one where one can globally choose a splitting into x's and x tildes. There would exist a global polarization. And the non-geometric one would be one where there's no global way of choosing which of the x's and which of the x tildes. There'd be inevitably there'd be some twist which wouldn't enable you to globally choose which one was which. So in this formulation, this way of thinking about T-duality acts just as to change the polarization. In the double space, it's perfectly well defined, and the problem is not with the big doubled space, but with our attempts to try and understand how one extracts the conventional physics from choosing 1/2 of the degrees of freedom. And so I'll just show quickly some slides, a quick flash up of the slide which shows the form of this kind of sigma model. It's constructed in terms of these 2D coordinates A, x. It's a double torus bundle in which the two connections we saw before, one coming from the metric and one from the B field, which are roughly speaking thought of in terms of these objects. I gave the precise definitions earlier, combine into a connection for this double torus bundle. And there's a metric, which is sometimes called a generalized metric, which is a 2D by 2D metric, which is made from the metric in the B field on the torus fibers. This was the GMN and the BMN we saw before. And one can show that this is precisely, which is covariant under duality transformations, and I'll say more about the transformation of these objects tomorrow. But I want to say something about open strings and D-branes in this context. So if a coordinate x is Neumann, the T-dual coordinate x tilde will be Dirichlet. In other words, if x satisfies Neumann boundary conditions, the T-duality changes Neumann boundary conditions with Dirichlet boundary conditions. So x tilde would be satisfied Dirichlet boundary conditions. And vice versa, if x tilde was Dirichlet, x would be Neumann. So, for example, if one looked at a 9-dimensional space, so a 9-dimensional torus times time, times a non-compact time, then there would be 9 Dirichlet coordinates and 9 Neumann ones. So, because there would be 9 x's and 9 x tildes, and of those, half would be Dirichlet and half would be Neumann. So in this context, we could think of, instead of splitting it into x's and x tildes, we could split it into Dirichlet and Neumann. And so in this context, we think of this, on this 9 torus, there's a universal 9-brane, which is a Lagrangian cycle in the double torus, which is an 18-dimensional torus. And a polarization chooses some number p of these directions, of the Neumann directions, as physical. And so this we'd interpret as giving a p-brane, and changing the polarization would change which subset of these directions we were taking as being physical, giving the physical coordinates. So in this way, we'd understand how T-duality, in this double picture, how T-duality changes a p-brane to a p+1 brane or a p-1 brane. So let's see this explicitly. So here we've got 9 Neumann directions and 9 Dirichlet directions. So a polarization will choose 9 of these 18 coordinates as physical. So if we chose all of these as being the physical coordinates, then all of the directions would be Dirichlet, and we'd say that we'd have a naught brane. If we chose, instead we chose one as Neumann and the rest as Dirichlet, we'd have a 1 brane, and so on. And so we'd have, if P of them were Neumann, we'd say that it was a P brane. And the T-fold transitions would allow gluing a T-P brane to a DQ brane. In a double picture, we'd be gluing universal 9 branes together smoothly, but the polarization would jump from patch to patch, and then that would mean that it would change the way we were viewing it, either a 2 brane or a 1 brane or a 9 brane. But the universal branes would be glued smoothly together in a way which everything fitted together. Finally, I mentioned that the constraint, which relates which is on these x's, which imposes that half are right movers and half are left movers. And so the constraint looks like this, where this A was the connection on this double torus bundle that I introduced. So we can choose a polarization locally over a patch splitting it into 2 sets of coordinates. And then we can think of this constraint as generating a shift in x tilde. And we can then gauge these shifts to get a gauge sigma model. So it looks a bit like the kind of formalism we looked at earlier. And then there's a topological term which gives rise to various factors of plus or minus 1, but taking those into account, it would then give an equivalence between the different formulations on an arbitrary Riemann surface. And it would extend the proof of the duality to the case where killing vectors are only locally defined, because that's what's allowed within these T-duality, within this T-fold story. And I should also mention that there's an alternative approach to looking at the quantization of this, which was formulated by Hackett-Jones some time ago using a canonical approach on but not on the general Riemann surface, just on the cylinder. And there's also various approaches in the literature which have looked at solving this constraint to get half the coordinates as right movers and half as left movers, and then quantizing them as Carl bosons. So how we do? So this is probably a good place to stop. And then tomorrow I'll talk about the double field theory and trying to extend, trying to look at the space-time interpretation of the kind of doubling we've looked at the level of the supermodel today. So I'll stop there. Thank you.
So do you think it would make sense to look at vertex operators on this boundary?
Yes, so hopefully there'll be time. If there's time, I'll say something about that tomorrow. If not, then please ask again, and I'll try and say something about that. But yes, one can certainly look at vertex operators in formalism. Indeed, I mean that's when I'm in some of the early work by Fadi Safin, he was essentially trying to do that.
Just a philosophical question. When you glue something around, you're supposed to impose some co-cycle conditions, and depending how you glue it, and the usual or triple intersections.
Yeah.
So when you deal with these T-folds, I mean...
Yes, thank you. That's something I was, to lack of time, I didn't go into the details, but in trying to set this up properly, one has to have consistent conditions in triple over and double and triple overlaps. And in particular, these are the same conditions for constructing a good 2 torus bundle over the base. So regarding that, so with where the transition functions are all in ODDZ rather than in GL2DZ. So it's precisely the same double and triple condition the double and triple overlaps that arise there, and I'll give them explicitly in one of the papers.
Okay, there are no more questions. Let's thank Chris again.